Welcome to a boss level question. If you've never done this before, let's get to it. So our old question, ON11, define simple harmonic motion. Okay, this one you should just know, okay, simple harmonic motion is A proportional to negative x squared. You need to talk about the proportional and you need to talk about the negative, x squared. Sorry, x. I was thinking of omega squared for some reason. So let's talk about acceleration that is proportional to displacement. If you want to be exact, you say displacement from equilibrium. Okay, so we got the proportional sign out of the way. Let's talk about the negative sign. What does the negative tell us? The negative just tells you that acceleration and x displacement is in opposite direction. So we need to talk about that. So second point, acceleration and displacement are in opposite directions. You know why we need them in opposite directions? We talked about this in the earlier theory video for this chapter. Go check out the playlist if you haven't seen it yet. But if you have something that is oscillating about equilibrium position, so like back and forth and back and forth and back and forth and back, the reason why it keeps going back to the middle is because there's some restoring force. For example, a pendulum. If you swing back and forth and back and forth, something always wants to pull it to the middle, to the middle, to the middle. That's the restoring force, and that's what makes simple harmonic motion. Okay, so if you have a displacement, let's say to the right, this is displacement. You're going to have an acceleration to the equilibrium position. So you see the arrow orange and red and green opposite direction, right? That's why I got negative sign. No? So here there is 2 marks. First one, if you talk about the proportionality, so that's acceleration proportional to displacement. This is number 1. And if you talk about the opposite direction, which is really the negative sign here, then that will be the second idea about simple harmonic motion. These two, very important, must remember, okay? Let's go to this oscillating plate now. Can this one oscillate in simple harmonic motion? Totally can. So a horizontal plate is vibrating. Just like zzz, like that, okay? There's some forces that will add up here. There's actually 2 forces. Who is having simple harmonic motion? The cube. We are looking at the cube that's going to go up and down and up and down and up and down and up and down, oscillating. The reason why I can do that is because there's 2 forces acting on this cube. Firstly, weight. This is constant. Because the cube is, 5.8 gram, I cannot get heavier or lighter, right? And there is a second force, which actually is the one that is changing. This is your normal reaction force. Normal reaction. I will just call this N. Sometimes we call this R. This is the one that is changing. Depending on where you are in this oscillation up and down. Okay, so there will always be a net force thanks to N that is changing that will point to the middle of this whole oscillation. We'll look at a simulation later. Anyway, so the plate undergoes simple harmonic motion with the frequency. I'm going to start listing up my values here already. This is F. Amplitude 3.0 millimeter. Oh, see the millimeter. Be very careful. Must convert later. This one I'm going to call this amplitude. Some past years equation will write this as X not amplitude. Just use whatever you know lah. Metal cube mass given to us. Calculate for the cube the energy of the oscillation. So how do we find the energy of oscillation? What energy? It kind of means total energy. They didn't specify kinetic or potential, so you mean total. So at some point you will have only kinetic. At some point, you will have only potential. Go check out the video if you haven't missed talk about this in the theory video. So total is basically Ke plus potential energy due to of the oscillation. But the easier one to find usually is Ke. At some points, there will be no Pe. At some point, and everything is just Ke, maximum kinetic, moving the fastest. Now, where is that going to happen? Let's list out the ideas. So, for total to equal to Ke, this will only happen at equilibrium position. Think of a spring lah, okay? When is the spring moving the fastest? At equilibrium, no, either moving up or down. You pull it down and you let go, it shoot up. And then you slow down, then come down again. Okay, so at equilibrium position, that's when the displacement is 0. That's where you have the fastest speed. You have highest V, highest kinetic energy. This is kind of a fact I write down so we can think about it. So how do you find KE again? Total energy at this point, total energy of oscillation is equal to kinetic energy is equal to half mv square. Hey, our good old friend, half mv square, very good. This one is not a spring, so you cannot simply say, oh, half kx squared. Maybe it's correct, maybe it's not, we don't know. Let's stick with Ke. So then we need to figure out what's the speed. We say it's higher speed, but what is the speed? How to plug inside here? Luckily, there is an equation given to us in the data formula sheet. I'm gonna write that here. At the start of every exam paper, you should be able to see an equation that says something like this. V equals to omega square root x naught square minus x square. This is the equation that will tell you what is the velocity at a certain displacement in your simple harmonic motion. And we can use this. I prefer to use, instead of x naught, I prefer to use a, so I'm going to use that. So we can say at highest Ke, you have x equals to 0. What is the velocity there? So I do a quick plug-in here. This will be omega times amplitude minus 0, equilibrium position. X equals to 0. So the velocity is maximum here. So I can, if you already memorize this Vmax equation, sure, you can use it. If not, you need to know how to get it from our data formula sheet here. So Vmax, the fastest possible speed, is at equilibrium, where x equals 0, and that's omega times a. Okay, let's plug that in here. So this will be half times m times omega a. Alright, let's continue. So we can plug in, wait, we don't know omega. Oh, we have f. F here can be found with our omega equals to 2 pi times f. Remember this. We can use this to find our frequency. So we sub in another equation. So this will be half m 2 pi f square a square. Ooh, it's a sudden change in color. Okay, so let's find the total energy now that we have all these things here. Need a little bit more space. We can go down a bit. Okay, here. Right, so half times mass, 5.8 grams. Grams, please convert to kg. So times 10 to the negative 3. This is going to be in kg, so a quick reminder. Convert everything to SI unit to save your pain. And this will be 2 pi times frequency, 4.5 hertz. I'll give it on the top right here. And we have, okay, that's it, square. Amplitude, 3 millimeter, so 3.0. Convert the milli. Please remember the power of 10. You gotta do that power of 10 right here, this pesky thing. Okay, bless. This is squared. And if you plug in everything correctly, you should get a value of 2.0865 times 10 to the negative 5 joules. That's a teeny tiny little amount of energy. It's still energy nonetheless, so we can write, how many SF should we write? Let's see the raw values given to us. 3.0 is in 2SF, 4.5 is in 2SF, 5.8 is in 2SF, everything 2SF. So I justify, if all this is given in 2SF, raw values, and I use those to calculate, so I'm going to follow that. 2.1 times 10 to the negative 5. I just follow the SF, they say 2, I do 2. Follow the least. You can do 2 or 3. So I write here 2 to 3 SF. It's okay. You can do this for all calculations. So 1 mark is the final answer. That's for sure. What else do we have? This A1 right here. We have one for the equation for total energy. You could either memorize this or recommended how you get that from half mv square. It's our old friend from AS. So you know your half mv square equation, and You must know your 2 pi f in order to get this one. So I make a link there. Then if you substitute everything correctly, that's the second mark here, substitution. Especially all the power of 10, the kg, the millimeter. Okay, this is in meter. Should write a reminder, meter. And you should get the final answer here. So that's 2.1 times 10, negative 5. Let's move on. This is where things get a bit strange. So amplitude of the oscillation of this plate is gradually increased. Haha. Okay. However, the frequency remains constant. So at one particular special amplitude, you get bigger and bigger, bigger, bigger until the point the cube lose contact momentarily with the plate. So when you say lose contact, it means like floating, you know. Floating, or aka no contact force with the plate, because you know the cube is on the plate. So you need to state what is the position of the plate, basically displacement, at the point where the cube lose contact. So where does it lose contact? Let's go back up to the picture a bit and see. You know this this diagram here, you can kind of do an experiment, you know. So this n, remember we said the n is changing, the mg is constant. You can try out this experiment with your phone. You have your phone with you, or if you're watching this on your phone, then pause the video, try it out. So you take your phone, put it on your hand, and you oscillate your hand. Okay, probably stick it out like that and you go oscillation. Okay, so keep a steady frequency. Now oscillate bigger and bigger, and my video is probably going to lag again. So I'm going to oscillate bigger, bigger, until some point you will feel the phone like just lift up from your hand. Okay, don't drop your phone, okay? Just sensible. Okay, so don't just keep oscillating. You feel your phone start to fly off from your hand. That's what I mean by lose contact. Gets bigger, bigger, it floats. So where does that happen? When your phone is at the lowest, or when your phone is at the highest? You feel when does the phone start to float? When you oscillate your hand up and down. Try it out and you will know the answer already. Okay, you can do this during exam. I'll just toss your eraser. But actually, your cube or your phone, the cube will lose contact with the plate at the highest position. So let's write this here. This is the highest position, also known as formally the place with maximum displacement. But don't forget, this is simple harmonic motion. This is equilibrium. Maximum displacement can either mean here or here. But you want to say highest position above equilibrium. So we clarify a bit what does highest position mean. So this maximum displacement above the rest position or equilibrium. Equilibrium. Okay, so this one is M1. When you talk about maximum displacement, but is it above or below? Above. That's when it will start to fly. So above rest position, that's going to be on this side. Because got two displacement, remember, above and below. So actually, this is our observation when we try to do the experiment. Actually, what is happening? What's the math behind this? Here's a kind of a nice visualization of what is happening. Okay, if you feel like the graph, wow, miss, what is this graph? Why so confusing one? You can ignore that one first. Look at the picture on the left. So this is a plug on a plate. Hey, thanks to this person who created this GeoGebra for us to see. So when we play, okay, I let the line go over first. The weight, if you notice, is just steady, same gram, 5.8 gram. But the normal force though, I know it's a bit hard to see, but when your box is the lowest, the normal force is the largest. See, the arrow becomes so big. So I'm going to pause that about here. So when your block is the lowest position, the normal force is very big because the block is pressing into the pen. When your block is at the highest, the normal force pretty much doesn't exist. Now, why is there? Why do they have two states like this? Because you remember, we always need a restoring force pointing to the middle of the or the equilibrium position. So if we go back to this picture, if I have some, I don't know, some box above equilibrium position, and I need a restoring force pointing to equilibrium, I already have mg. Mg is pretty big. I don't need much normal contact force. I mean, I could have a really tiny one. That's my normal contact force between the plate and the cube. So that my restoring force overall, all this pointing downwards, is going to form my restoring force. On the other hand, if you have the box at the bottom, you need to restore to equilibrium position. There needs to be some kind of restoring force pointing towards the equilibrium position. So mg is not going to give you that. Mg is just always pointing downwards. So your normal force have to compensate for that. Give it a big fight to fight against mg to provide that normal contact force. It's a little bit like circular motion contact force thing. Okay, so this one, where is n the smallest? Highest position. Because mg already contribute a lot to the restoring force. Why do I say spring? Fs Fs is restoring lah. Let's rename this restoring. Restoring. Okay, so this point is important for next part. Part 2. Or next part. Oh, there it is. Okay, so amplitude of this oscillation. How do we find the amplitude? They didn't give us graph. They didn't give us much values actually. So where is the amplitude? Amplitude, we say maximum displacement. We don't have much info to find out A. Because you say, Miss, shouldn't it be 3.0 mm? Wait. No. That is part 1. Now this part, we are talking about the one where it loses contact. Where it loses contact because your amplitude is getting bigger and bigger, and you want to find the amplitude when you lose contact. So this is a different amplitude from first part already. Cannot say 3 mm. So we need to think of, okay, box will lose contact when it's at the highest point above equilibrium position. And there is going to be mg, which is the restoring force to push you back to equilibrium. But there's not going to be a normal contact force. So I'm going to write here n equals 0 from the plate. So it looks like it's stuck there, but actually it's just above the plate, floating. Try again now, okay? You oscillate your phone in your hand, you feel it. So we know our good old equation A equals to negative omega square x. This is acceleration. Amplitude, if we can find x, what is the acceleration at maximum displacement when it lose contact? What's the acceleration? I think the hint lies in the force diagram on the left side. So let's look at the force diagram. The net force acting on a block, we usually say net force equals to mass times acceleration, right? I think we can find the net force. The net force, there's only one force, mg. That's just it. And that will cause a block of certain mass to accelerate. So that is going to be, what's our clue here? Mass is the same now, okay? So g is the acceleration, which is 9.81. We are on planet Earth near the surface. Yeah, ms negative 2, sorry. So now we can use our simple harmonic equation. Acceleration equals to negative omega square x. Okay, so at maximum highest position, where we lose contact, that's where we're going to find our amplitude, because we know the acceleration. So this is going to be 9.81. The negative sign, the negative sign, we often ignore it. Okay, so because it depends on where you define positive, negative. So I'm just going to say ignore the negative sign. It's okay. This will be 2 pi f. Omega is 2 pi f. Yeah. 2 pi times the front part. You go back and see the front. This is 4.5 hertz. And the x, okay, this is highest position, right? So we call this the amplitude. Big A. Or some people prefer to use x naught. Also can. So we find the amplitude here when you lose contact. Remember, we are looking when you lose contact. Where is the amplitude? this would get you 1.2271 times 10 negative 2. Very small amplitude. So here you can round off to everything looks like 2SF, right? Other than the constant 9.81. So we're going to stick to this 1.2 times 10 negative 2. This is how you can find this, this amplitude when you lose contact. So 1 is for final mark as usual, okay? And 1 is for your usage of this equation, the simple harmonic motion equation, and you use 9.81 inside. Then only you can get that C1 mark, right? So go play around with the simulation a bit more to stare at it, oscillate the phone on your hand, feel when your phone starts to fly away from your hand. That's the losing of contact. But I think that's all for this question. Hope that helps you in understanding a little bit better when you have stuff oscillating on the plate. And make sure don't get trapped by questions like that. So that's all for this video. I will see you in the next one.